Hi there and welcome to my AP Physics 1 lesson on circular motion. Let's call this part 3. This is going to be mostly about Newton's universal law of gravitation, Coriolis effect, and some other effects that, kind of bigger picture stuff. So here we have a little animation of a spinning Earth and some dude on that Earth. So I want you to picture yourself on the Earth, or any object on the Earth for that matter, and actually moving across the Earth. I suppose that I could make this person a different color. Can I do that? Let me see if that makes sense. If I make them red with envy, a little bit easier to see on top of the globe. There we go. Okay, so looks good. So now this person is standing on the globe at the equator. So imagine this person being on the equator, and they go through one day. So let's watch like Africa go by, since we have, okay, so there he is. And so just in like half a day, for example, he goes by, and look at how far he went. Versus when it comes by, what if you're down here, right? So okay, Africa's going by, and in the same amount of time, they don't go, in fact, I went too fast. They don't go as far of a distance, along their path in that same amount of time. So you should recognize that just standing on the surface of the Earth, you are moving faster along the tangent just due to the fact that you're closer to the equator. And so there's some very interesting effects that occur because of this. For one, you have a force of gravity that's acting towards the center of the Earth. And I think that everybody kind of intuitively understands that. It's pretty straightforward of a thought. So you have a force of gravity acting towards the center of the Earth. Let's go ahead and say that you're standing, okay, fine, you're at the equator, and there's a force acting towards the center. But you also have this effect where, because you're at the equator and you're moving very quickly, if you can imagine, just imagine, for example, let me just go ahead and make another sort of circle. If you are standing, let's make this a circular sort of path. Okay, fine. So there's some sort of force that's pulling you towards the center. But if you're on the outside of the circle, as it goes around, let's say you're moving in this sort of direction at this moment in time, that's your tangential velocity. Unless you're stuck to the surface, right? So in fact, let's imagine this thing's out in space, no gravity. Let's say you're velcroed to the surface of this rotating cylinder. Before we had talked about you being on the inside of it. Did not mean to make that. I meant to actually grab him. There we go. So before we were talking about if you're on the inside. If you're on the inside, it's a very different scenario, because you want to keep moving along the tangent, but the inside surface is going to prevent you from doing that. But now you're on the outside surface. And let's say that you're velcroed to this surface. How strong would the Velcro need to be? You can kind of consider that. That's why you would have to consider centrifugal forces. Because if I just know that the Velcro can handle so much pull here on Earth, it should be the same amount of pull in this scenario, and I have to figure out what is the centrifugal force, which is the reactionary force to the centripetal force. Okay, so you have a velocity along the tangent, and then you can figure out what the acceleration towards the center is necessary in order to keep that motion. But can you imagine that essentially your motion along the tangent is kind of unweighting you? It wants to pull you away from the surface. So by standing here on the Earth, let me get rid of these. By standing here on the Earth, you are effectively being unweighted because of the very sheer fact that you are moving along the tangent, because you want to keep moving along the tangent. Imagine if the Earth were to just start spinning faster and faster and faster and faster and faster and went out of control. You would shoot off into space. So imagine just the very fact that the Earth spins around once per day, it unweights you. And so with that in mind, you are unweighted less standing here. So you're telling me that the acceleration of gravity is greater at the poles than at the equator? Yes, but that's not the only reason why. Can you imagine, or can you even do it? Do me a favor, pause the video if you need to and try it now. Stand up, put your arms loosely and, kind of wiggle your arms, relax your arms, and spin around, right? You spin around, and I don't have room to do it here, but if you let your shoulders and arms relax and you spin around in a circle, what happens to your arms? They kind of lift out, don't they? Because your arms have inertia, they have momentum along the tangent, and they want to keep moving along the tangent. And so as you spin, they're going to keep trying to do that, just like a ball on a string, right? Same exact reason. And so what happens to the Earth? Well, the Earth is solid-ish, but it's big. And so because it does have some fluidity, is that, there's a word there that I can't say. So it has some fluidity, some amount of fluid. Don't make fun of me. So it has some amount of like fluidness to it. And so the word's in my head and I can't get it out. So as the Earth spins around, because it has some amount of fluidness to it, it actually becomes wider in the middle and it becomes shorter. It's like a middle-aged man, which I sometimes feel like these days since I'm stuck at home so much. And so it becomes wider in the middle, and that's what actually happens. So the sphere of Earth isn't a perfect sphere. It's a spheroid. It's sphere-ish. And so it's wider in the middle. And so wait, that means that you're actually farther away from the center of mass, which means that there's not as much gravitational pull because you're farther away from the center of mass. Versus being over here, you're closer to the center of mass because the Earth is more this kind of shape. So not only do you have a greater gravity at the poles because of this whole effect of you like being spun off of the Earth, at least a little bit, but you're also even closer to the center by being at that part at the poles. So yes, the acceleration of gravity is greater here than it is here. This is also why the United States typically and historically has launched their spacecrafts from Cape Canaveral, Florida, because it is about as close as we can realistically get to the equator in the United States, because just by simply being there at that location, you are traveling at 400 or 500 meters per second in the eastern direction simply by just standing there. So all they have to do to get in orbit is to get a rocket and shoot that rocket in the eastern direction. They almost always shoot eastern direction, and in order to get in orbit, and you need to go fast enough to go there. So you just need to go to a certain speed and then you'll be in orbit, which we'll actually tackle in a little bit. All right, so let's kind of tackle some other conceptual issues here. So here we have a guy who jumps into a hole drilled through the center of the Earth, and I want you to consider that. And we're going to get to this equation in a minute. So he jumps in, and at first, he is going to accelerate at a rate of about 9.8 meters per second squared. He's going to accelerate, and he's going to go down. And as he goes through, he's going to accelerate and then slow down, right? And at some point, he pops out the other side, and then he goes back through. Let's imagine that this hole is vacuumed out of all air, so there's no air resistance. What is his acceleration like through the hole? And where is it most? Where is it least? So basically at the surface, technically it's like just below the surface, is your greatest acceleration. As you go through, it becomes less and less and less until actually in the middle, his acceleration is actually 0. Why would it be 0? Well, because, let me see if I can choose some color that would show up. Yellow does a fairly good job, and you know what, I'll make my if I can, I'll make my dots bigger. There we go. So I'm just going to put some random yellow dots here that represent just very random molecules of the Earth. And so what you should recognize is that each and every single molecule of you and every single molecule of the Earth has some amount of pull towards it. Okay, it has gravity. And so you're being pulled this way, you're being pulled that way, and towards each one. Now the closer the molecule is to you, the greater the force of gravity, because that's the way gravity works, and I'll get into that in a bit. And so actually the strength of the force would be sort of the inverse of my length of the arrow. Not completely, because again, I'll get back into that, but you get the idea. And so you're being pulled into all these different directions equally because you're at the center of mass of the Earth, and so your acceleration due to gravity would actually be 0. In fact, you'd be truly weightless. You know that in space, you're not actually weightless. It just seems that way because you're constantly falling, you're constantly accelerating. There is a net force acting on you in space. You're orbiting the Earth. It takes you 90 minutes to orbit around once. However, if you're at the center of the Earth, you're not accelerating. You're actually weightless there. So consider those issues. Okay, let me get rid of this stuff. So as you go through, you would have an acceleration of 0 at the middle, but you would have a really high velocity, right? High acceleration, and but you're moving slow, and you go faster and faster and faster, but the rate at which you're increasing your speed is decreasing. Don't get confused by that. You're going faster with each moment, but the amount that you're going faster isn't that much, okay, with each moment. And then you go across the middle, you're going really fast, and you would start to slow down just a little bit. And now you're starting to slow down more. And now you're starting to slow down more. Now you're slowing down really a lot until you peek your head out. Here, let me spin him around. You peek your head out and you like say to somebody on the other side of the Earth, and you're like, hello, and you like go back in the hole. And that's what would happen. Is you would just kind of like rubber band back and forth, kind of like a spring. It would be a simple harmonic motion kind of thing. Something we haven't gone into yet, but we will. Let's focus on this equation. So this is effectively Newton's law of universal gravitation, where the force of gravity acting on you due to some sort of body is going to be equal to big G, get into that in a moment, times m1, m2 over r squared, where m1 is the mass of object 1, and let's just say that that is Earth, okay? The m2 would be the mass of the second object. In this case, that's going to be you. So let's say that you're standing at the surface of the Earth. What is the force of gravity between you and the Earth? Well, wait a minute, we know that, don't we? I mean, isn't that just mg? So the force of gravity is not only this, but it's also just simply equal to mg. But whose mass and whose gravity? So if you are m2, then this is also m2. If this is your mass, then this is your acceleration due to gravity. So this here is the 9.8 meters per second squared. We don't have to set these two things equal, but we certainly can. And you're like, but wait, the m's cancel. Yes, that means that your acceleration of gravity, the rate at which you accelerate, is completely independent of your mass. Instead, it is completely dependent on the Earth's mass, which makes perfect sense. So what that means is when we observe objects out in space, let's say that we look at an object like Jupiter, how do we know what the mass of Jupiter is? So what we would do, if I can back up and erase some of my slash marks, so what we can do is we can basically say, okay, rather than it being G, okay, let me erase that, instead I'm going to put A. That'll be totally fine. It is G, but I'm going to put A, and you'll see why, because I don't want you to confuse it with 9.8 meters per second squared specifically. Instead, I'm going to look at the acceleration of a moon of Jupiter, so Titan or whatever it might be. So if we look through a telescope and we see this acceleration, we observe it, and we can see that Titan, a moon, is accelerating at a certain rate, and we can determine that through the telescope. And we can also, through the telescope, determine how far away it is, so what its radius is. So these two things we can actually determine simply by looking at the moon of Jupiter through a telescope. And the moon, its mass cancels out. This is a constant, it never changes. So now, the only thing that is unknown, and we don't need this part, right? That's just there to get us set up. The only thing that is unknown is the mass of Jupiter, and we can determine what the mass of Jupiter is quite easily. This is exactly how it's done. Okay. What is G? Well, we want to be able to express, let me cut this part out for a moment, ignore it. I want to be able to convert between mass, measured in kilograms, distance, measured in meters, and force, measured in newtons. How do I do that? Well, I need some sort of conversion factor, which is what G basically is. It's known as the universal constant, the gravitational constant, and so big G is equal to 6.67 times 10 to the negative 11th. And it has some pretty funky units to it that I honestly don't even ever remember. I could go through this equation and figure it out, but I'm not terribly concerned about. I'm just concerned about the number. You should know what the number is, but specifically, look at how small it is. What does that mean about the force of gravity? it means that the force of gravity is very small, that you need a lot of mass in order for it to have any significant value. So please consider that. Let me switch gears for a bit, and let's look at Kepler's laws of motion. So this is Kepler, poorly written, but Kepler, Johannes Kepler. So Kepler was essentially a mathematician who became an astronomer and made some very precise measurements of the planets and things like that. And so this was long before they really knew exactly what was going on in the heavens. That's what they called it. And so what he had realized, first off, is that he certainly agreed with the heliocentric model of the solar system, that the sun is at the center. But it was part of his job. He was one of the people who actually kind of proved that this is the way that things worked. So he basically said that all planets move along an elliptical orbit, okay? An elliptical, okay? It's an ellipse. An ellipse is a shape. It's like an oval shape, but it is mathematically something that can be determined, right? Yeah, it's just oval shaped. No, this has actually got some mathematical properties to it. So basically, imagine that this is a string. In fact, I should make one more part to the string. So you make a loop of string, okay, and I'm going to attach it. And imagine that you were to have this on a piece of paper and you take your fingers inside of that loop, right? So I'm going to take some headphones or whatever. And so you tie a loop and you put your fingers inside of the loop. And then you take and this is very hard for one person to do. So you take your fingers inside of the loop and then you trace, okay? You trace around, trying to trace, like if you know how to make a circle, right? You just take like one focal point and you can trace a circle, right? You're doing the same thing, except instead of making a circle, you're making an oval. It's an ellipse. And instead of having one focal point, you now have two focal points. And so that's what's happening here. So here you have one focal point, that's where the sun is. And then here you have another focal point. And then where you're tracing is where the planet, that's its path is. And so I have F1 and F2 being the focal points. What is at F2? That's a great question, glad you asked. Nothing. There's nothing there. There's nothing at the second focal point. And you're like, that doesn't make any sense. Because what happens is the planet will move faster here as it gets closer to the sun, and it will slow down and move slower as it's farther away. And if you think about it, it should actually make sense, because if you think about it in terms of energy, when it's close, it has less potential energy. So where did that potential energy go? It went into kinetic energy. And then out here, slows down, right? It's farther away. It has less potential energy. Excuse me, it has more potential energy. And so it should slow down, and it will have less kinetic. And so that's basically what Kepler's second law effectively says. His first law basically saying that the orbits are elliptical, and then his second law basically says that you have equal time intervals between each of these positions. So between 1 and 2 and between 3 and 4, these are equal time intervals. And so as the planet goes from here to here, if you were to shade in the sweeping area between these, its orbit and the sun, these areas would be the same. And in order for this to be mathematically true, it must be moving fast here and slow here. Okay, so that's what the planets do. And if I can get a little animation going for you, that'd be great. In fact, I think that's this here. So let me get that going. All right, so here's a little online animation. There's a little animation that I'll just run, and so I can change the distance. Here, let's do this, and it should be fairly elliptical. You notice it'll be really close and then really far. So I like it. Let's watch. And you notice what it's going to do is it's going to make these equal time intervals, and it's going to shade in the areas. So equal time intervals. Look at how the shaded areas. Whoop. There you go. So you'll notice that when it is close, it zips around. So not all planets have the same amount of eccentricity is actually what it's called. So if it's more eccentric, then it's more elliptical. So Earth is pretty close to being round-ish. There's times when it's a little bit farther and times when it's a little bit closer. So that is when it's at its certain positions. Let me think about those names. Let's see here. So helio means sun, so when it's close, it's at its perihelion position, and when it's far, it's at its aphelion position. I always remember that because, if you were to hold a kitten close, it'll purr, perihelion. It's cheesy, I know. And then when the moon goes around the Earth, or really any planet really, it'll be at its perigee position when it's close, perigee, and when it's far, it's at its apogee position. And you can also talk about those in terms of rockets and their movements and satellites and things like that. And so why is it that the moon looks closer, or why does it look bigger in the night sky at certain times, certain months? It's because it's at its most closer to its perigee position. And then here is Kepler's third law. So this is the time it takes for the planet to go round. So for Earth, that would be 365 days, or 1 year. And oftentimes the way that you'll do it is you will relate it to Earth. So let's say that Earth is planet A, and so this would be perhaps 1 year. And this would be the 1 astronomical unit, which is the distance between the sun and the Earth. We just call that 1 AU. Or you can actually put it in meters, and this could be days or seconds or whatever you want it to be. And then you would have the time that it takes for planet B to go around and the distance. And so you can pretty easily use this. Just make sure you keep track of the square and the cube, and this is how you can actually determine, given that a planet is at some distance, you can figure out how long it'll take for it to go around the Earth. All right, so let's take a look at something else here. All right, so there's a couple of things that I'd like to end on. One is the math here, just doing a little bit of substitution that you should have ready and available to use. So this can be really useful in some of our, really to anything that deals with circular motion, but it can deal with some orbital stuff. So this time period here would be the time it takes for the planet to go around or orbit, whatever it might be, and that sort of thing. So here we have acceleration is v squared over r, and v is of course 2 pi r over t, where if you consider any sort of circle, right, the circumference of that circle is 2 pi r, so the distance, the time it takes for it to go around once is the distance, and the time it takes to go around once is of course big T. So we could do that substitution, put it in place of v, and this allows you to work out to 4 pi squared r over t squared. So you don't have to memorize this, but it's good to be able to do this substitution at any time. And so with that, I'm going to leave you with one more math thing and end on this. And I would like you to think about, in fact, let's go to here. So I have already shown you this equation. Let's go ahead and use it. So for a satellite that will orbit around and is going to go around, we want to know how fast, right? What is the velocity required for something to be able to orbit at some altitude? Now, low Earth altitude is usually about 2,000 kilometers, right? So that's 2,000 kilometers, which is 2 million meters. So keep that in mind. We have a radius of the Earth that is, I think that's, actually had to look that up. That's 6.3, I think that's 6.37 times 10 to the 6th meters. And then we have a mass of the Earth that we know, right? The mass of the Earth is equal to 5.98-ish or 5.97 times 10 to the 24th kilograms. All right, so you don't need to know these numbers, and I'm not even really going to go through the whole thing, but let me kind of show you something. So if we have the force of gravity is equal to big G times m1 m2 over r squared, and we said that this is also equal to m2g. So let's follow along this idea. Well, m2 cancels, so let's say that this is some sort of satellite that is out here, right? So some sort of satellite, right? It's got its solar panels and all that jazz, and it's going around at some speed. How fast does it need to go? Well, gravity is the force that is acting towards the center. It's causing it to accelerate towards the center. But that's a centripetal acceleration, isn't it not? Which acceleration is equal to v squared over r. In this case, it just happens to be gravity that's causing that acceleration. So I'm going to do that substitution. This is, right, this is v squared over r. Okay, so I don't need this anymore. Acceleration is v squared over r. So this is equal to this. So let's solve for v. It's that simple. So v is equal to, let's see, we have big G times m1 over r, and take the square root of it. And that's it. Big G is the 6.67 times 10 to the negative 11th. M is the mass of Earth. That's what this is. R is the radius of Earth, plus the additional bit. Don't forget that part, because that's something that can throw you off, because that's where the satellite is. It is a distance away from the center of the Earth that is equal to the radius of the Earth plus its altitude. Add those two numbers together, throw it all in, and you get a number somewhere between 7,000 and 8,000 meters per second, which is how fast an object needs to go in order to be able to orbit. It takes 90 minutes for them to go around, and by the way, just a little tidbit of fun math, it takes the exact same amount of time for this guy to go back and forth if he were to travel through the center of the Earth in my example from earlier. So if this satellite is overhead when he jumps in, he's going to go through, come out the other side, and 45 minutes later, the satellite here will be over there as well. That's kind of crazy, right? All right, well, that's it. I think that's going to cover it. I know it was a lot on this one. It's long, I'm sorry. And so we'll, in fact, it's not it, because I definitely have some other examples I'll go through, so I'll send that out too. All right, take care. Have a great one. And I hope this stuff is actually interesting to you guys like it is me.